Hi, the following is a conversation with the Lord Professor Martin Rees, a leading cosmologist and astrophysicist. He has conducted influential work on galaxy formation, cosmic jets, black holes, gamma-ray bursts, and speculative aspects of cosmology. Professor Rees is the Astronomer Royal and the past president of the Royal Society. He is a prominent scientific spokesperson and author of popular science books. In 2012, he co-founded the Center for the Study of Existential Risk, which is a research center at the University of Cambridge intended to study possible extinction-level threats posed by present and future technology. In this podcast, we cover some of the aspects illustrated by Professor Rees in his book on the future, and these include nuclear warfare, climate change, biotech, pandemics, and artificial intelligence. Due to these challenges, Professor Rees believes that we will face a growing tension between three things we want to preserve: privacy, security, and freedom. I know this is a polarizing topic, and please consider that this is not a debate, but it's an opportunity to hear what one of the most prominent scientists and policymakers has to say about global threats, including the current situation. So whether you agree or disagree, please leave a comment below. We will be releasing this podcast in episodes every 1 or 2 days. So if you wish to access the full podcast immediately, please join us on Patreon. Otherwise, subscribe and turn on the notifications so that you will know when the other episodes are available. So this podcast will be also available on Spotify and Apple Podcasts, so you can find the links in the description below. And now, here's my conversation with Professor Martin Rees. Okay, good morning, Professor Martin Rees.
Good morning.
So I'd like to start our discussion with maybe if we could discuss a bit about what was your major scientific contribution, and if you had to pick up a paper among your 500 plus publications, which one would you choose?
Well, I find it difficult. I'd like to say really that my contribution has been to be involved in various debates over the last 40 or more years, which have clarified how our universe began and also clarified the nature of some of the extreme objects in it, the objects that involve neutron stars, black holes, cosmic explosions, etc. So I've written a lot on all those themes.
I was checking some projects online, and I found this Illustris TNG project, which is a fascinating attempt to simulate galaxy formation and evolution. And these simulations basically start from collections of particles and the laws of physics, such as gravitational interactions and magneto-hydrodynamical interactions. So my question is, I don't know if this makes sense, but what would it take to simulate the emergence of the laws of physics from the Big Bang?
Well, we don't understand how the basic laws originate, but we know that the expanding universe is governed by those laws, and we can trace the Big Bang and its history right back to when the universe had been expanding for about a nanosecond. Before a nanosecond, it's hard because the energy of every particle is higher than the energy we can achieve in the Large Hadron Collider, the biggest accelerator. So the physics is not well understood for the first nanosecond. But from that time onwards, we can understand how, as the universe expanded and cooled, the different processes took place. We can understand how helium and deuterium were formed when the universe was a few minutes old. And we can understand how the radiation, the thermal radiation, was produced in the early universe, and it cooled down. And these obey the laws of physics we understand. And it's been quite easy to understand how a homogeneous universe, just uniform gas, would behave. But, of course, what we want to do is to understand how structures emerge. And we know that the early universe wasn't completely smooth. There were some places slightly denser than average, some less dense than average. And as the universe expanded, then the overdense regions lagged behind in their expansion and eventually condensed out. And this is how we believe galaxies formed. And what's one of the great triumphs of science in the last 25 years has been to observe the fluctuations in the universe at an early epoch. This is done by looking at the background radiation over the sky and seeing the small non-uniformities, and to put that in as your initial conditions in a computer program and work forward. And the good news is that working forward, you end up with a universe rather like the one we live in. And this is done by putting into the calculation gravity and gas dynamics and maybe some other things. And this has been great progress in the last 20 years because it needs good computer power. And until 20 years ago, it was not possible. And of course, more generally, astronomy has benefited hugely from computer simulations because if you're a particle physicist, you can actually crush particles together and see how they behave, whereas we can't actually crash real galaxies together, but we can, in the virtual world of our computer, see what happens if two galaxies collide or if stars explode, etc. And that's how we have been able to see if our models do represent the real world. And we now have a picture for how galaxies evolve, which comes from simulations, but which is tested. And in fact, we can test it very well because we look at galaxies now, but we have an advantage over paleontologists in that we can actually see the past. So we can compare our simulations with the universe now, the universe 1 billion years ago, 2 billion years ago, 3 billion years ago, etc., by looking at more and more distant galaxies where the light set out earlier. So we have quite good evidence that we understand the broad outlines of how cosmic structures evolved from the amorphous Big Bang, which started off very hot and dense with small fluctuations in it. But of course, all progress in science leads to new questions and new mysteries. And what we'd like to know is the crucial process which happened right in the very first nanosecond, when the physics is uncertain, because it's those processes which determine how the universe expands and the fact that it contains atoms, dark matter, and radiation. And that's still a challenge.
In your books, you spoke about having a sort of a cosmic perspective towards the problems of the world. And you became interested in topics related to existential threats. And you discuss these things in your book on the future. And I've also read your other book, which is Our Final Hour, where you talk about these issues. When did you become interested in these topics?
Well, of course, that's quite separate. There's a huge gulf between the cosmic scale and the terrestrial scale. But I'd always been interested in politics and going back to student demonstrations for disarmament, anti-Vietnam War and things like that when I was a student. And later in my career, I got involved more in disarmament through things like the Pugwash conferences, which are links between scientists in the East and the West during the Cold War. So I got involved in that. But later in life, I had more opportunity and more obligation, in fact, to engage in policy and politics because I spent 5 years as president of our Royal Society, which is the UK's National Academy of Sciences. And that, of course, covers all the sciences and their policy implications. And so during that period, and since then, I've spent a fraction of my time on things which are not astronomy, but more general policy related to what's happening here on Earth now.
You're also the Astronomer Royal. What's the role of the Astronomer Royal?
It's just an old title. It used to be the person who ran the observatory, the National Observatory at Greenwich, near London, but that became a museum when it became possible to build telescopes on higher and drier locations, Hawaii and Canary Islands, etc. But they kept the title, but it's just an honorary title.
You're also the co-founder of the Center for the Study of Existential Risks here in Cambridge. What's the purpose of this center?
Well, this is something which I've become more committed to over the years. In my early book, Final Hour, which you mentioned, I drew attention to the fact that we were, in the world, becoming vulnerable to new classes of threats that weren't important in the past. And in my new book on the future, I explain this in more detail. And the main point that I make in these books is that this century is special. the Earth's been around for 45 million centuries, but this is the first when one species, the human species, has been numerous enough and empowered enough to actually determine the fate of the planet. We can affect the Earth's climate, the flora and fauna on it, and of course we are interconnected through air travel, internet and all that. And so for the first time we run a risk of catastrophes which could cascade globally. And this is something which is new. And these are less studied than more local, conventional risks. And I wrote quite a bit about that. And our centre in Cambridge has a focus on these extreme, high consequence, low probability threats, which are becoming more important and looming larger. And of course, the COVID-19 pandemic that we're having this year has, of course, made people take these seriously, because that in itself shows how some unexpected threat can have global consequences. And we clearly are learning that we need to prepare more to cope with catastrophes of that kind and to minimize the chance that they occur. Pandemics are just one category, but there are other things like a breakdown in the electric power grid in a large region, either accidental or a cyber attack, and other global catastrophes which could come about. And so what our centre is doing is collecting a group of people who will focus on these and draw on the sort of convening power of a great university like Cambridge to bring more expertise to bear on these questions.
I mean, in terms of politics, does it cover the full spectrum of politics? Is it a bipartisan sort of organization?
Well, it's not party politics, but it does include social scientists and economists, of course. That's very important. But of course, we are experts who advise politicians, and of course we do engage with politicians and participate in parliamentary affairs and try and raise the profile of these issues on the agenda compared to the way they were. So this is something which we think is important, because politicians obviously have a crowded agenda. They tend to focus on the immediate and the local and what happens before the next election. The COVID-19 pandemic is a wake-up call, because this is a crisis which they never prepared for properly, and indicates what can happen. What we need to do is to make sure that governments do prioritise these. There's an important maxim which I like to quote, is the unfamiliar is not the same as the improbable. And because these things have never happened before, that doesn't mean they won't happen. A pandemic, in retrospect, wasn't all that improbable. There had been others a bit like it in the last 20 years. And so we need to prepare more for these things. And of course, there's a class of threats which are caused collectively by our heavy footprint on the planet, and this is of course climate change, and we know that is going to have severe consequences. But the political problem of dealing with that and prioritizing that is that the main effects are going to be a few decades in the future. They're not immediate. It's not like the COVID-19, which has immediate effects, and so we're rather like the frog in the pot of water that's being heated, which doesn't realize that it's going to boil until it's too late to save itself. And we've got to think further ahead to do this. And of course, the problem for politicians is that they tend to focus on the more immediate concerns, and also on the concerns for their constituents. And of course, climate change is going to have a bigger effect in parts of Africa than it does here. And so to get politicians to prioritize what happens in Africa 30 years from now is hard. And the only way this can be done is if the public cares. And so they respond to public pressure. So that's why raising the agenda on these long-term issues among the wider public is very important.
And you guys also collaborate with the SAGE, which is the Scientific Advisory Group for Emergencies here in the UK.
Not directly. There's some overlap, obviously, but and there is a a parliamentary committee at the moment which is going to discuss better ways in which this country can prepare itself for these different kinds of threats. So we are obviously in a university, in all of science, trying to be useful when we can. And clearly these extreme threats are now being taken more seriously.
Yeah, so when we talk about threats from space, I mean, we have threats from comets, asteroids, solar flares. I mean, for those things, there isn't much we can do at the moment. I mean, maybe in the future we could think about changing the path of a meteor or a comet or whatever. So I guess the only option now is building underground bunkers or Faraday cages. Have you built one under your home?
No, but because asteroid impacts don't keep me awake at night. And the reason for that is that we understand their probability. We understand how many asteroids there are, etc. And we know it's a possibility, but a low probability. And we know that that probability is no higher now than it was 10,000 years ago or 10 million years ago. And so it's small. And indeed, as you say, we might be able to do something to protect against some within this next century. And so it's important to try and map out the orbits of all the asteroids that come near. But it's not a top priority. What is more worrying are the classes of threats which are getting more probable year by year, like pandemics, cyber attacks, and things like that. I worry far more about those and about engineered pandemics and things of that kind. They're the big worry. Solar flares are in a slightly different category because they're natural phenomena, but they had no effect on life on Earth until 150 years ago when we had electricity. But they do, of course, now have a potentially serious effect. And so they are something which we want to predict a bit better by observing the sun carefully, and also, of course, to mitigate the effects of by the way we construct the electricity grid, and also the way we harden the electronics of spacecraft.
And also we have plans in place in case something happens, which is taking all the government or Her Majesty the Queen to the bunkers. They have similar programs in the US where they have these emergency plans which were from the Cold War, I guess, when there was a threat of nuclear war.
Yes, well, so certainly there have been those threats, but the key question is to decide what is the appropriate response to any kind of catastrophe. Of course, we know the problems of hospitals being overwhelmed by a severe pandemic. We know that if electricity failed for a few days over a large area, that would lead to complete social breakdown, because the lights going out is the least of our problems. All electronics and everything would fail. And so we need to absolutely minimize the likelihood of those things happening, and also have emergency plans in operation to deal with them.
Thank you for listening to this conversation with Professor Martin Rees. So if you enjoyed it, please leave a comment below, like, subscribe, turn on the notification bell, and support this channel on Patreon. This podcast is also available on Spotify and Apple Podcasts. You can find the links in the description below. Thanks for watching.